Welcome back, AP Statistics. This is part 3 of chapter 19. We're going to be doing a complete hypothesis test, and we are really going to slow down and pay attention to each step because a hypothesis test is quite a process, but you will absolutely get used to it. There is a bit of a learning curve, though. We start, of course, with the hypotheses themselves, which we've been discussing quite a bit in the first 2 lessons. We begin by stating the null and alternative hypotheses. Let's consider this scenario from our textbook. A large city's DMV claims that 80% of candidates pass driving tests, but a newspaper reporter's survey of randomly selected local teens, 90 to be precise, who had taken the test found only 61 who passed, right? Now, 61 out of 90, with a little bit of rounding, you can confirm that that is just shy of 70%. That's a bit less than 80%. So, does this finding suggest that the pass rate for teenagers is lower than the DMV reported? All right, now objectively, that sample proportion is lower, but is it significantly lower? Or is it just maybe a little bit lower, and if we were to take another sample, it wouldn't be quite as low, and maybe we just happen to get a low sample. So we're going to write appropriate hypotheses. Here's what they would be. We're going to say that we assume the passing rate for teenagers is the same as the DMV's overall rate of 80%. So that is the assumed population proportion, unless there is strong evidence, of course, that it's lower. So, appropriately, the null hypothesis reads, the assumed population proportion is 80%. But the alternative says it's less than 80%. Well, why not equals? Why is it strictly less than? Because we are trying to see if the findings suggest the pass rate is lower, all right? That means we are performing a one-sided alternative type of hypothesis test. We're only concerned about the left tail. Proportion being less than 80%. We only care about that left tail. It's a one-sided alternative. Now let's move on to what's Success Kid doing? Well, we'll see why he's there in just a moment. We're going to talk about modeling. All right, now this kid right here at the bottom right is modeling success, but let's see what we're modeling. Specify the model to be used for the test. For this section, we're going to be using a normal model, and we're going to be performing a one proportion z-test for the population proportion. So it's a z-test for the population proportion, or we could just say one proportion z-test. Of course, we need to make sure the right assumptions can be made and that the appropriate conditions are met. I warned you about this. Every time we do just about anything for the rest of the year, we need to check conditions. So there is an assumption of independence we need to make. Data values must be independent of one another. How can we confirm this? Here comes the important part, the conditions. The randomization condition. Data were sampled at random or treatments were assigned at random in the case of an experiment. Also the 10% condition. We cannot sample 10% or more of the population without violating independence, right? So in order to assume independence, we need to sample less than 10% of the population. Also, the sample size needs to be big enough. How do we check that? Well, it's the success-fail condition with a slight twist. When testing for the population proportion, which we're doing now, we need to expect at least 10 successes and 10 failures. And if this sounds familiar, that's because it is, except for that word expect. Sometimes we need to observe successes and failures, like in the case of a one proportion z interval. But in this case, we need to expect some number of successes and failures, namely 10. All right, we need to pay close attention there. Let's apply our knowledge of the conditions to our scenario. So, large cities DMV claimed 80% of candidates passed driving tests, and a reporter has results from a survey of 90 randomly selected local teens who had taken the test. All right, so from that information, we can see if the conditions for inference are satisfied, right? Randomization. 90 teens surveyed were a random sample of local teenage driving candidates. Basically, the problem said so. 10% condition. Well, we can safely assume 90 is fewer than 10% of teenagers taking driving tests in a large city. Now, if this were a small town, we may not be able to make that assumption, but we can make this assumption. Success-fail condition. Pay close attention to this one. We expect n times p sub 0. What is p sub 0? P sub 0 is the assumed population proportion. Remember what that is? That's the 80%, okay? So n times p sub 0 is n times the assumed population proportion. It's what we say p is equal to in the null hypothesis. So p is equal to this p sub 0 fella, all right? That sub 0 refers to the null hypothesis, okay? So n times p sub 0, n is obviously 90, and the assumed population proportion is 80%. So we put the 80% there, so we say 90 times 80% is 72. 72 successes, n times q is 90 times 0.2, that's the complement of 0.8, that would be 18 failures. Both are at least 10. That is clear enough. So the conditions are satisfied. We can assume independence and a large enough sample so that we can use the normal model. Okay, so we are now allowed to use the normal model, and we are going to perform a 1 proportion z test. Let's move on to the next part. The mechanics. We want to determine whether the data we collected to test the null hypothesis is reasonable or if it's unusual, assuming the null hypothesis were true. If the data we collect seem reasonable, not far off from the 80% we predict, then we should not reject the null hypothesis. But if our data are unusual, assuming the null hypothesis were true, well, maybe that assumption's false. Maybe we should reject the null hypothesis and support the alternative hypothesis. But again, we can never, ever, ever support a null hypothesis. That is impossible, right? Never, ever, ever can we support a null hypothesis. So we determine the reasonableness of our data in light of the null hypothesis by finding the p-value. That determines how likely it is that we got data like we did, that got results like our data did, assuming the null hypothesis is true. If we assume the null hypothesis is true, how unusual are our data? That's what the p-value tells us, okay? And precisely, how do we get this p-value? Well, we use the calculator. We find p-values in the graphing calculator. That's what that red text was for. So here's when we're going to get the p-value in the graphing calculator. A large city's DMV claimed that 80% of candidates passed driving tests, but a survey of 90 randomly selected local teens who had taken the test found only 61 had passed, so just shy of 70%. What is the p-value for the 1 proportion z test? All right, now to recall, our hypotheses are H0, null hypothesis, p equals 0.8, H sub A, alternative hypothesis, p is less than 0.8, okay? So to do this, to find the p-value, the likelihood of getting that 61 out of 90, assuming this 80% were actually true, how unusual is it for us to get 61 out of 90 if this were the gospel truth? Well, we're going to go to the calculator, we go to stat, we go to tests, and we go to 1 prop z test, all right? Not 1 prop z int anymore, though we will be visiting that later in this section. one prop z test, and we're going to find the p-value. And in our calculator, we need to remember to select p less than p sub 0, because that's what the alternative hypothesis says. P is less than our p sub 0, our assumed population proportion, of 80%. So we're going to need to remember to do that. Here we are back at the calculator. Let's go to Stat. We're going to go to Tests, and we're going to go down to one prop z test. Hit Enter, and we are immediately greeted by p sub 0, our assumed population proportion. We would type 80%. X is the number of values in our sample that satisfy some characteristic. In this case, it would be the number of applicants who passed their driving test. That would be 61 out of the total of 90. Remember, we are looking for an alternative hypothesis of p is less than 0.8. So we're saying less than 0.8. Let's highlight that, okay? So this tells us right here that our alternative hypothesis is p is less than our assumed population proportion of 0.8, right? Now I'm going to go down to Calculate, hit Calculate, and bada bing, bada boom, we have our p-value. Our p-value is approximately 0.002. That is very small. Let's see how to interpret it. Before we formally interpret our p-value, I want you to have an idea about how low this p-value is. Notice this bell curve right here. This bell curve models the sampling distribution for sample proportions, which is centered at the assumed population proportion and has a standard deviation of square root of PQ over N. Notice I'm going some number of standard deviations out to the left and right of my assumed population proportion. How many do I need to go to the left, because I'm considering the left tail for this study, to get to my proportion from my sample, which is 61 out of 90 equals 0.678, just shy of 70%. Well, I have to go 1, 2, 3 almost standard deviations. 3 standard deviations? On the normal curve, that's no man's land over here. There is nothing going on around 3 standard deviations away from the assumed population proportion, all right? That is how far down the bell curve we are with our result of p-value equals 0.02, all right? There's something going on. There's some kind of issue with this 80% number the DMV gave us. Let's talk about it. So that p-value being 0.002 means that assuming the true proportion of students who pass their test is 80%, the likelihood of 61 out of 90 students passing, the data that we got, the likelihood of getting that is 2 in 1,000. That is very, very unlikely. Now, assuming that we collected data in a reasonable manner, and as we've said before, there's no reason that we didn't. We passed all of our conditions to assume independence and large enough sample size. What's suspicious is this 80% number, all right? We have strong evidence, a low p-value, that this number is suspect, all right? Because if this were the true number, we would have a very low likelihood of getting data like ours. And since our data collection is good, that proportion is suspect. So, we make a conclusion. To conclude our test, we need to decipher the p-value. A low p-value, of course, means we should reject the null hypothesis, and our data are not likely to be replicated if the null hypothesis were true. And of course, a high p-value means that we should not reject the null hypothesis. Our data could, if we had a high p-value, reasonably be replicated if the null hypothesis were true. So here we go. Let's interpret formally what our hypothesis test is saying, okay? So what can the reporter conclude? And how might the reporter explain what the p-value means for the newspaper story? Here, what are we getting at here? Most people do not understand statistics. How can we make this result relatable to the everyman, as it were? So here's how the textbook says it. And of course, they do a really good job. Because the p-value is 0.002, 2 in 1,000, and it is very small, I reject the null hypothesis, says a writer of our textbook. These survey data provide strong evidence, strong statistical evidence, that the passing rate for teenagers taking the driving test is lower than 80%. So the difference is significant. Okay, the difference from 80%, what we assumed, is significant. And we have strong evidence to say this 80% is suspect. The true proportion is lower. If the passing rate for teenage driving candidates were actually precisely 80%, we would expect to see success rates this low only about 1 in 500 times. That's 0.2%, right? 2 in 1,000, 1 in 500. Samples of this size. This seems quite unlikely, you don't say, casting doubt that the DMV stated success rate applies to teens. Note, a good conclusion has 2 key features. 2 features that you should include in your conclusions for your hypothesis tests. First, we state whether the p-value leads us to reject or not reject the null hypothesis. We need to explicitly link the p-value and our decision to reject the null hypothesis and support the alternative, or not to reject the null hypothesis. And second, we apply that decision to the context of the problem. If you just say we reject or not reject the null hypothesis and don't appeal to the context of the problem, you are losing points in the free response, I can guarantee you. So you need to link the p-value and the decision you make regarding the hypotheses, and then you must apply that decision to the context of the problem. This book answer does a great job of both of those things. Perhaps it can be a template for you.